Okay, cool. Welcome everyone to the 6th week of Intro to CP. This week we're going to be doing an intro to dynamic programming. And the slides link is here, tinyurl.com/introcp6slides. And the portal code is Domino's Pizza. Cool. So as usual, we have our Discord forum, Intro to Competitive Programming in the ACM Discord. And so after the workshop, if you guys have any questions or want us to look over your code for one of the contest problems, then feel free to either send one of the officers a message on Discord or message in this Discord channel. And we also have a couple events coming up. Bruin Quest is going to be this weekend, and that's a puzzle hunt that's a collab between Hack, ICPC, and Cyber. And so that's going to be Saturday and Sunday. The opening ceremony is at 10 a.m. and check out the Bruin Quest Discord. The invite link is here. And I think all the events, including the opening ceremony, are just going to be held on the Discord. So check that out. And then we're also going to hold office hours this week. It's going to be tomorrow from 1 to 2 p.m. And so office hours is going to be sort of a pretty chill thing. You can just come if you have any questions about this week's contest or any of the other contests that we've done. If you want to go over some of the problems or review any of the concepts, then feel free to check it out. You can, well, it will probably use the same Zoom link, I think, and we'll have some officers here to answer any questions. And then we also have our mini contest. So because of next week is Thanksgiving, we're not going to have any meetings next week. And then this will be our final workshop. And then 2 weeks from now, on December 3rd, so week 9 Thursday, we're going to host a mini contest, and it's going to be 3 hours long from 7 to 10 p.m. And we'll have 7 or 8 problems. So it'll be, I guess, your first competitive programming contest. We'll do each of the problems will sort of relate to one of the week's workshop topics. So it'll be a good way to sort of review all the stuff that we've learned this quarter. Cool. So let's start with this week's workshop. It's going to be dynamic programming. So first we're going to do our first we're going to go over recursion. And then we'll talk about 2 dynamic programming concepts, memoization and tabulation, and we'll do 2 example problems as well. So to start off with recursion, recursion is a pretty broad topic, and if you haven't heard about it before, you'll learn about it in CS32. But for the purposes of dynamic programming, one super important part of recursion is something called a recurrence relation. And a recurrence relation is a way of defining a sequence using 2 things. One is base cases, which are the initial values of the sequence. And the second thing is sort of defining in a mathematical way how you can get from one term to future terms. So the idea behind a recurrence relation is that you start with your base cases, and then from there, you have this way of getting to future terms from current terms, so you can get to future elements of the sequence using the base cases. So let's look at a couple examples of that. So these are 2 super common sequences that I'm sure most of you have heard about. One is factorial and the other is Fibonacci. So factorial is essentially the product of all the numbers from 1 to n. So n factorial, for example, is n times n minus 1 times n minus 2 all the way down to 1. And it can actually be represented in a recursive way. So the base case is 0 factorial is equal to 1. This is just sort of by convention. And then from there, 1 factorial is 1, 2 factorial is 2, and so on and so forth. And the recurrence here is that n factorial is equal to n times n minus 1 factorial, because n minus 1 factorial is the product of the numbers from 1 to n minus 1. And then if you multiply that by n, then you get the product from 1 to n. And the idea behind the recurrence here is that if you know what n minus 1 factorial is, then that can tell you what n factorial is just by multiplying that by n. And that means that you start with 0 factorial is equal to 1. And then to get to 1 factorial, you just multiply by 1. And then to get to 2 factorial, you multiply by 2, and so on and so forth. And that's a way of constructing the sequence. And a similar thing is true for Fibonacci, where you have the base cases f0 is equal to 0 and f1 is equal to 1. And then your recurrence for Fibonacci is that each Fibonacci number is equal to the sum of the previous 2, starting with f of 2 is equal to f of 1 plus f of 0. And that gives you the sequence 0, 1, 1, so on and so forth. Cool. So that brings us to a topic called recursion. And this is now going from math to computer science, this is how you would implement a recurrence relation using code. And the idea behind recursion, and it's a lot more complex than this, but for the sake of this workshop, the main thing is the idea that you can call a function within itself. And so this is an example of factorial. And you can sort of call the factorial function within itself. And what that means is that you have your function, you have your base cases implemented. So this is like an if check where if n is equal to 0, if n is a base case, then you exit, and otherwise you print out, or you do your recurrence relation. And to sort of step through how this would work, the idea is that, I guess for example, first, this is just the base case. So if you did 0 factorial, that's like factorial of 0. And in that case, the if branch passes if n equals 0 passes. So you just immediately return 1. You don't have to even worry about this factorial being called a second time. But if factorial is larger than 0, if it's not a base case, then it's a little more interesting. So for example, if you do factorial of 1, then then n is not equal to 0. So you'll go to the else statement, and then you return 1 times factorial of 0. And what calling a function within itself means is you essentially loop back to the beginning of the function. So when you call factorial of 0 within factorial of 1, you loop back to the beginning and then calculate factorial of 0. And it turns out that you already know factorial of 0 is 1. So then factorial of 1 ends up being 1 times 1, which is 1. And then 2 factorial, we'll also get to here return 2 times factorial of 1, which is 2 times 1, which is 2. And so on and so forth. You'll get 3 factorial is 6, and 4 factorial is 24. And yeah, so it's really important, though, to make sure to add base cases, which is something like n equals 0. Because if you don't do that, then you don't really know when to stop. And the idea is that a recursive function, when it hits the name of the function that was being defined, it goes back to the beginning and restarts. And if you don't have this if statement, then you're going to go down, hit factorial, go back to the beginning, and then sort of go in an infinite loop. And the only way to get out is in this base case, where if n is equal to 0, you return something without even hitting factorial again, so without even going back. So that's the only way to really exit the loop. So base cases are super important because of that. Cool. So next, let's talk about the Fibonacci sequence. This is another recurrence relation. Once again, the terms, the base cases are f of 0 and f of 1 are 0 and 1. And then from there, f of n is equal to f of n minus 1 plus f of n minus 2. So that gives you the sequence here, 0, 1, 1, 2, so on. And the idea is that we can use recursion to print out this, or to calculate Fibonacci numbers too. And so this is how you would do that. It's a pretty similar idea to factorial. First, you have your base cases. In this case, there's 2 different base cases because we had both f0 equals 0 and f1 equals 1. And then from there, the recurrence relation is pretty much done in a similar way, where you just pretty much return whatever your sequence's recurrence relation was. So in this case, fib of n is just equal to fib of n minus 1 plus fib of n minus 2. So you just return both of these. And so yeah. Let's actually go into this in a little more detail just to sort of understand how recursion exactly works. And so this is the actual way that program will execute when you call, for example, fib of 4. And so when you call fib of 4, n is equal to 4, and it goes through these 2 if statements. In both cases, n is not less than or equal to 0, and n is not 1 because it's not one of the base cases. So you hit the recurrence relation. And your program then returns fib of 3 plus fib of 2. But so first it would do fib of 3, and then here it's already hit the Fibonacci function again, and it wants to evaluate it immediately. So what ends up happening is before it even gets to fib of 2, it pauses and it goes back to the beginning. And now Fibonacci is being evaluated using 3 as your parameter for n. So it pauses, it doesn't do fib of 2 next. It starts to figure out what fib of 3 actually is. And fib of 3 ends up being the same sort of recursive thing, where now n is 3. Again, it doesn't match the base cases, and now it prints out fib of 2 plus fib of 1. And so you get to fib of 2. Again, it pauses instead of going to fib of 1 immediately, and then it goes back to the beginning, and then you get fib of 1. And this time when you get to fib of 1, it actually does match a base case. It matches n equals 1, and so it just returns 1. It doesn't have to branch down anymore. It just returns 1. And then that goes back up to fib of 2. And then fib of 2 can finally resume. It was going to return fib of 1 plus fib of 0, but it paused when it had to calculate fib of 1. So now it resumes, and it tries to calculate fib of 0. This time again, it reaches a base case, which is 0. And then now you have both these terms evaluated, and then you just return the sum of them, which is 1. And you get to here. And now fib of 3 can resume again. So now fib of 3 will call fib of 1, and that will evaluate to 1 because it's a base case. And then now fib of 3 is done. It just returns the sum, which is 2. And now fib of 4 can resume. And remember, fib of 4 was supposed to return fib of 3 plus fib of 2, but it got paused after doing fib of 3. So then it does fib of 2, and the same sort of thing happens where it branches to a fib of 1 and fib of 0, which return 1 and 0. And then they sum up to 1, and finally fib of 4 can evaluate to 3. Cool. So the next thing we're going to do is a poll, just to check understanding of this. Jacob's going to create a poll about these sorts of recursion trees. And I recommend maybe using a piece of paper to write down the tree, just because it can get a little bit complicated, but we'll take a few minutes to work on this. Cool. So it seems like there was a lot of different answers chosen, but the actual answer was 11. And the idea is that you want to sort of draw a tree. It can be pretty difficult to trace through all of these, all of the different calls without drawing a tree. And the tree is actually pretty similar to the tree with Fibonacci. The only difference is now your occurrence relation is a little bit different, and so are your base cases. So your base cases are now if n is less than or equal to 2. So basically n of 2, n of 1, n of 0, anything less than or equal to 2. And your recurrence relation is also slightly different, where instead of f of n minus 2, you now have f of n minus 3. So as an example, let's say we were doing f of 6, which is the question in the poll. Then it sort of branches out into 2. It branches out into f of 5 and f of 3, which are f of n minus 1 and f of n minus 3. And then each of these is evaluated separately using the exact same recurrence relation. So f of 5 is evaluated to f of 4 and f of 2. F of 4 is then evaluated to f of 3 and f of 1. And f of 3 is then evaluated to f of 2 and f of 0. They should say f, not fib, sorry. But so the idea there is that every single sub element of the tree branches out using the exact same recurrence relation, using f of n minus 1 plus f of n minus 3. However, the recurrence stops at specific numbers, and if you notice, those are 2, 1, and 0. So at f of 2, it doesn't branch down anymore because you hit your base case. And the idea is that when you hit your base case, you don't continue using your recurrence relation. You just stop there and you return 1 in this case, or in other cases, it's whatever your base case is, you'd return that. But the idea is that you only make function calls when you're not satisfying your base case. And whenever you're not satisfying your base case, then you branch out to further smaller ends, essentially. So in the case of f of 6, you branch out into f of 5 and f of 3, and then each of them continues to branch down until you get to your base cases of 2 and 0, and then you stop. And similarly, here you stop at 1, here you stop at 2, here you stop at 2, and here you stop at 0. So every leaf node in this graph, or in this tree, has to be either a 2 or a 1 or a 0. And then each of these returns 1. And then from there, you go back up. And the poll is essentially just asking for people to count the number of things in this, which ends up being 11 in total. Did that make sense to everyone? Does anyone have any questions so far? Yeah, feel free to ask in the chat. You can stop me later as well if you want me to go back to this. But cool. Okay, so I guess we'll move on from this, and we're going to go back to the Fibonacci sequence. We'll talk a lot about the Fibonacci sequence with DP. And so going back to the Fibonacci sequence, we showed example code of how you would implement Fibonacci using recursion. And to remind you guys, that was if n is less than or equal to 0, then return 0. If n is 1, return 1. So those are your base cases, and then otherwise return your recurrence relation. And we had this tree that shows the function calls for fib of 4. This is really similar to the tree from the poll. And as it turns out, the number of things in this tree ends up being doubled in every single row, every single level of the tree. The first time you have 1 function call, then you have 2, then you have 4, and then you stop for the case of fib of 4. But let's say we were doing something like fib of 30 or fib of 40, then you would have tons and tons of levels. Each time the number of elements per level is doubling. And what that ends up being is that the runtime of the problem, you're going to have to run 1, then 2, then 4, and so on. And it turns out that that means that the runtime grows exponentially, which means, let's say you're doing fib of 4, then you have like 4 levels approximately. So that would be around 2 to the 4 total. 2 to the on the order of 2 to the 4 different computations that you have to do, which is only like 15 or 16. It's not too many computations in this case. Exactly, it's 9, which isn't too bad. But let's say we did, we wanted to calculate fib of 40 or fib of 30. Then suddenly 15 or 16 computations becomes a billion or a trillion computations, because exponential growth turns out to be super, super fast. And if you imagine an exponential function, it sort of starts really slow and then it suddenly shoots up and goes really high. And turns out to the 30 is approximately a billion. And that's going to TLE really quickly, which is really bad. And so that brings us to something called memoization, which is the idea that we can reuse values that we compute. And it turns out that in this graph, there are sections of it that are repeated. So for example, this section, fib of 2, fib of 1, fib of 0, this whole, these 3 elements is identically repeated over here, where you again have fib of 2, fib of 1, fib of 0. And this is like, this identical repeat is kind of unnecessary because we first calculated fib of 2 over here, and we found that fib of 2 is equal to 1. And it's not going to change over here. We're going to calculate fib of 2 again, but the value is the same. Fib of 2 is always going to be 1. So the idea is that we can actually just reuse the value. Because we calculated it here, our program should already know what fib of 2 is. And calculating again can sort of take time. And the idea is that here we're calculating it twice, and the amount of times we calculate it will grow exponentially. So if we save it, then we can cut down from exponential to just calculating each thing once. And so yeah, we can just return from here. We don't need to branch down to fib of 1 and fib of 0 because we already theoretically can figure out what fib of 2 is by calculating it here. And so how do we actually implement that? You can't automatically in C++ just remember what in informal terms, remember what the value of a function is. You actually have to save it yourself. And the idea for that is using something called a memoization array. And this ends up being a global data structure that's used to save values. So that's this vector over here. And it's created outside of any function. If you notice, it's outside of the main function, it's outside of the fib function. And the reason for that is because you want the values in the memo function to persist past any call of fib. So by putting it in the putting it as a global variable, it'll persist past any function call of fib, and it's also accessible within fib. If you put it in main, you could make it accessible to fib, but it's a little more work. And so yeah, that's the way you would create a global data structure. And then the idea behind the memo array is that you save every value that you calculated as an element of the array. So for example, memo of 0 would correspond to the 0th Fibonacci number, memo of 10 would correspond to the 10th Fibonacci number, and so on and so forth. And you sort of populate it as you calculate. So initially, you set all the numbers to be -1, which means that they're not calculated yet. And then you sort of go from there. So as an example, in your base cases, this is step 4, you set mem of 0 to be 0 and mem of 1 to be 1, which means that you've calculated fib of 0 to be 0 and fib of 1 to be 1. Oh, how do you know how big to make your memo array, right? So the idea is that you only need to make it as big as the largest n that you want to calculate, because if your goal is to calculate fib of 30, then you only need to store 1 through 29 because, or 1 through 30, sorry, because you don't really benefit from knowing what fib of 31 is because it's never going to be used. So the idea is that in the caddis problem, you'll usually like see into like a variable n, which tells you like the bounds of the problem or some other variable that's similar. And the caddis problem will usually tell you what the bounds of your problem are. And you only have to make your vector as big as that. So in this case, I made it 100, but it can really be whatever is based on the caddis problem's bounds. But yeah, so going back to the fib function, so there's two parts to it now. And the first is that you want to check if you've calculated a value before. Isn't it? Right, so yeah, if you want to do it based on n, then yeah, you're going to have to declare your memo vector in your main function. And there's actually a function called resize that can do that if you want to do it there. But the easier way, I think, is you can just sort of like caddis will tell you how big n can be, and you can just be safe if you want and just, yeah, it'll say 1 is like less than equal to n is less than equal to 10,000. And then to be safe, you can just set this number to be 10,000. So just the upper bound for n, essentially. Or you can do it in main. I think you have to pass your vector by reference into the function though then, and that becomes a little bit more complicated. So I would recommend just doing it globally and then using the largest size to be safe. Cool. So yeah, so in the Fibonacci function, there's two steps. One is you want to check if a value is already saved before computing. And what that means is that if you've already calculated fib of n, there's no reason to calculate it again. And you sort of save that as in your memo array as element n. And if it's -1, it means it hasn't been calculated yet. If it's something other than -1, so like a positive number or 0, then it means that it's been calculated and set to a value. So you first check if memo of n is not equal to -1, which means you've already calculated fib of n, and then you just return what value you had previously calculated. And otherwise, you return memo of n is equal to fib of n minus 1 plus fib of n minus 2. And so this is actually doing two things. The first is calculating fib of n minus 1 and fib of n minus 2, and then it's adding them up. This is the recursion part. And this is also the recurrence relation being implemented in code. And this part is how you actually calculate the Fibonacci numbers. And then the second part is saying memo of n is equal to this. So that what that's doing is it's sort of, once you calculate a Fibonacci number, you're saving it inside memo of n. So it's after computing a new result, you save it. You don't just want to forget about it after your return. You want to remember it globally, so you store it in your global memo array. And then finally, you return whatever value you stored. And this is just a shorthand. You could also just do memo of n is equal to that and then return memo of n. This is just a shorthand to do it all in one line. And there's a question in chat, can we put base case in fib? And the answer is yes, you can. If you did that, it would work. You could just put like two if statements here. If n is equal to 0, then return 0. If n is equal to 1, return 1, and then have these things here. And either one of them works. The idea is that if you have your base cases here, then You kind of have to do your base case checks every single time you call fib, but that doesn't matter too much. I think either way works. This is just a common way of doing it, but you can also put it in your fib function if you want to. It's kind of up to you. Cool. Does anyone have any questions on this before we move on? What's the complexity? Okay, so the complexity for this function is going to be order of n, because ultimately what ends up happening is that let's say you called fib of n, then you're going to have to calculate the numbers fib of 0, fib of 1, all the way up to fib of n at least once to figure out what fib of n is equal to. And then from there, you never have to calculate those again because you already know what they are. So it's going to be order of n to calculate it the first time. And then another key thing to note there is that let's say your problem first asks you to calculate fib of n, and you do that. Then let's say later in your problem, you want to calculate fib of n over 2. Well, it turns out then that to calculate fib of n, you stored all of the values in the memo array from 1 all the way up to n. So what that means is that if you wanted to calculate fib of n over 2 the second time, it's going to be order of 1 because you've already calculated it before and you've saved it before. So the idea is that the overall order of growth is going to be order of n, but if you want to calculate multiple times, the first time is the only time that it's order of n, and then afterwards you can just calculate constant time. Yep, no problem. Cool. So if there's no more questions, we're going to move on to our first problem. The contest link for the example problems is here, tinyurl.com/intro-cp6examples. And as usual, we have IO templates as well. Yeah, like Jacob said in the chat. Cool. So we'll give you maybe 5 or so minutes to work on this example problem. We will, cool. So let's go over the solution now. So just to go over quickly the overview of the problem, the idea is that there are letters displayed on a screen, and then every time a button is pressed, the letters sort of transform. So the first time you have the letter A displayed on the screen, then each time the button is pressed, every letter A on the screen transforms into a B, and every letter B on the screen transforms into a B and an A. So you start with an A, then the A becomes a B, the B becomes a BA, the B first becomes a BA, and then A becomes a B, so you get BAB. And then here, the B becomes BA, the A becomes B, and the B becomes BA, so you get BABBA, and so on and so forth. And the idea is that you want to keep track of the number of buttons being pressed. The first time you have B and then so on, and you kind of get like a table like this, and each time you want to know how many A's there are or how many B's there are. And then given a number of buttons pressed, so a number K, you want to output the number of A's and the number of B's. And so looking at this table, there are actually some patterns that are that you can notice just from the table itself. And the reason for some of these patterns, for example, one of them is every A that's in the table, every like number of A's, it had to have come from a B in the previous round, because every A is only generated through a B that's transformed into it. So that gives us this pattern where the number of B's in the previous round is equal to the number of A's in a certain round, because every A came from a B in the previous round. So for example, the 2 here becomes a 2 here, 3 becomes 3 here, 1 becomes 1 here, and this kind of holds for every single value k. And so yeah, we get a pattern here, a sort of like diagonal carry from the number of B's to the number of A's in the table. And then for the number of B's, it's pretty similar. The only difference is that B's can come from either B's or A's from the previous round, which means that the number of B's in the next round comes as a combination of both the number of A's and the number of B's. So there's just another pattern that you can notice where you have 1 A and 1 B becomes 2 B's in the next round, 2 A's and 3 B's becomes 5 B's in the next round, and so on and so forth. So it's sort of adding the two numbers from the previous one, the combination of that gives you the number of B's in the next round. So there's two patterns, and that's sort of, it sort of hints at a recurrence relation that tells you the number of A's and B's of a certain round from the previous round. And that's sort of a theme of dynamic programming, is trying to find a recurrence relation and then using that in your code. Cool. So you can sort of use these patterns, for example, to find the number of A's and the number of B's if we press the button 6 times. And we just sort of plug in the patterns. 5 becomes 5 A's in the next round. And you combine the 3 and 5 and you get 8 B's in the next round. And the idea here is that we have 5 A's and 8 B's, but we didn't even have to calculate the sequence of B's and A's in the letters displayed. And this is really important because as it turns out, the number of A's and B's grows exponentially. And pretty soon there's going to be a huge number of A's and B's, and it's not really realistic to actually go through all the characters and swap each B with a BA and each A with a B, because the number of characters is going to become really huge. And instead, using these patterns is really useful for this problem. Cool. So yeah, the next step in this problem is sort of representing these numbers and these patterns in a more mathematical way. And a trick to doing that is sort of using a variable, so sort of defining a sequence. And we'll just focus on the number of B's, because in this problem it turns out to be a little bit easier, but you could also focus on the number of A's if you wanted to. And so we're going to define a sequence. We're going to call it B of k, and so B of 0 represents the number of B's in row 0. B of 1 would represent the number of B's in row 1, and so on and so forth. And so we already know B of 0 is 0 because we're given at the beginning that the only letter displayed is A. And we know that there's one A to begin with. This is just sort of base cases. And then from here, using our pattern, B0 carries down to here. And we know this is equal to 0 too. But over here, we know that B1 is equal to 1 because, first of all, there's one B here, but also you can sort of use the same pattern where you combine these two, 1 and 0, to get to 1 here. And then you sort of rinse and repeat. So once again, B1 gets carried over, and then here we have B2 is equal to B0 plus B1. So B1 plus B0 is equal to B2. And then again, B3 is equal to B2 plus B1, and number of A's is B2. And so on and so forth, you get this sort of pattern. And looking at this side a little bit more closely, you can see B5 is equal to B4 plus B3. B4 is equal to B3 plus B2. And this just sort of keeps on going. So for any large n, B of n is going to be equal to B of n minus 1 plus B of n minus 2. And then also B of 0 is 0 and B of 1 is 1. And I hope you guys can sort of see this resembles a really common sequence, and it's a sequence that we talked about earlier, namely B of n is equal to f of n, because the base cases are the same, the recurrence relation is the same, adding the two previous numbers to get to each number. And so as it turns out, B of n is equal to f of n for all n. So these two sequences are the same. And that means that we can sort of rewrite this in terms of f. And we see that the number of B's is f0, f1, so on and so forth. And then the number of A's is slightly offset, where you start with 1, and then you have f0, f1, and so on. And that means if we generalize to a certain k, then the number of a's is equal to f of k minus 1, and the number of b's is equal to f of k. And from there, we've already figured out how to use memoization to solve for a certain Fibonacci number. And all we actually have to do is add these two lines to the end of the Fibonacci number code. And the first one is taking an input. So you declare a variable k and input into it. And then after that, you just output the two numbers that we wanted to calculate, fib of k minus 1 and fib of k. And that translates directly to this table. Cool. Did that make sense? Does anyone have any questions about this before we move on? Cool. Okay, let's move on. So next I want to ask, how would you calculate f of 10? This being the 10th Fibonacci number. And if you think about it, the obvious answer, I guess, is to use your code, because you already have code that can calculate any Fibonacci number. And so we could calculate f of 10 using this and just see out fib of 10 and then run this code once and you'll calculate fib of 10. And this does work, but if you were to do this by yourself without a computer, you'd probably do it a different way. And the idea is that the code first tries to calculate fib of 10. It doesn't know how to do it yet, so it goes and it breaks it down to fib of 9 plus fib of 8. And then it breaks that down further using a sort of tree. And you start from fib of 10, then you go all the way down to fib of 0 and fib of 1. And when you hit those numbers, then you return your base cases. And then after that, you sort of resume and you go all the way back up the tree. And that's a little bit indirect because you already knew your base cases were 0 and 1. And there's not really a point to starting at fib of 10 and then going down and then going back up. You could have just started by going up. So, and if you didn't have a computer, you'd probably do something like this, where you sort of wouldn't think recursively. And instead, you would use something like a table, and you'd start with your base cases and then just work your way up from there, because every term is equal to the sum of the previous two. You know that the next one is 1, then 2, then 3, and so on and so forth. And it's just a really quick way of just sort of counting and filling up a table until you get to the one that you want. And this is something called tabulation, if you do this using code. And so tabulation is a similar technique to memoization. The only difference is that memoization is top down, which means that you start at your the one that you want to calculate, and then you break that down into subproblems using recursion and recurrence relations. And you break it down until you get to your base cases, and then you work your way back up. Versus tabulation sort of takes out that level of indirection, and it starts from the bottom and directly goes from the bottom up until you hit your desired value. And so tabulation can often be easy to write in the sense that you don't actually need to use recursion. And especially for people who aren't too familiar with recursion yet, haven't taken CS32, tabulation might be a better approach. It turns out that tabulation and memoization generally, especially for the intro to DP problems that we'll be doing, generally the two of them will be pretty similar in terms of time complexity and also space complexity. So you don't have to worry too much about which one you use for most of these problems. At some point, you'll see that there are some DP problems that for which tabulation is better, some for which memoization can be better. But for these, you can probably just do whichever one you want to, whichever one's easier to code. Doesn't it follow easily by induction? Yeah, you could use induction to, I'm assuming this is for the example problem, but yeah, you could use induction to sort of prove it in a more mathematical way if you wanted to. Using the table is just kind of an informal way of sort of figuring it out. Oh, never mind. Okay, cool. Okay, so how would you rewrite your solution to use tabulation instead? And so this is the same code, except we're using tabulation instead. It's the same, it's solving the same problem, and this solution would also work for problem A. And the idea is that suddenly you don't have your Fibonacci function anymore, you just have your main function. So you've kind of removed the whole thing with recursion altogether. And now you instead of having a memoization array, you have a table instead. And so the table is also just an array. For all intents and purposes, it's the same sort of thing. Now you can actually use like k or n instead of you just using the maximum bound if you want to. But now suddenly all you have to do is first to set your base cases and then sort of fill in the table in a similar way to like how we did a few slides ago where we just filled in the table. You just iterate through the table for every I up to K, and you just sort of plug in the recurrence relation directly. So it's just sort of a more direct way of doing it, where if you have a recurrence relation, you just directly plug in the recurrence relation to fill in the table. And then from there, you can just print out the desired output. So you just print out table of K minus 1 and table of K minus 2. Actually, this should be table of K minus 1 and table of K, not K minus 2, sorry. But yeah, the solution with tabulation is pretty similar. You just can avoid recursion by filling in a table instead. And that's actually a pretty common thing where loops and recursion can sort of be used interchangeably in a lot of cases that you'll see in CS32. Cool. So now we're going to move on from Fibonacci numbers, and we're going to talk about some more complex recurrence relations. And it turns out that the ones that we've been looking at for Fibonacci and factorial, they're all using only one variable, and that's why we can use a one-dimensional vector. And the idea behind one variable is it's like a sequence where you're just defining based on one variable n. So like fib of n minus 1, it's all using that one variable n. But as it turns out, and this is probably where DP becomes a little bit harder, is that recurrence relations aren't always in one variable. Sometimes you can talk about 2D structures or 3D structures and things like that. And recurrence relations can get more complicated really quickly, and they can often have more than one variable. And when you have more than one variable, your code has to be changed a little bit, where like in session 3, we talked about vectors and how you can have 2D vectors. And this is sort of a similar concept. For example, if you had a 2D recurrence relation, then you'd want to use a 2D vector. And this is sort of like just a review from session 3. This is how you would create a 2D vector, vector of vectors of ints. And then this is the first dimension n, and then the second dimension m. And then this is what you would initialize all the values to. And so let's look at an example of that. And one common example of that is Pascal's triangle. And this is it's a common triangle. It's used in combinatorics. And the way that it's created is that the first row or the first column is all ones, and then the last column is all ones of the triangle. And every other number, like 2, 3, 4, 6, 10, they're defined as being the sum of the two numbers directly above it. So the 3 is given as this 1 plus this 2. So you take the 1 and 2, and then you add and get 3. Similarly, the 6 and 4 give you 10, and so on and so forth. And so that's Pascal's triangle. It has a lot of interesting combinatorics applications, but for us, let's just say we had a function s, and let's say it had two numbers. The first one would tell you which row you're talking about, and the second one tells you what entry it is. So for example, s of 4, 2 would represent the fourth row in the second entry. So in this case, you'd go to the fourth row, second entry, and you'd find that it's a 3. And so that's how we're going to define s. And then using this function, we can actually create a recurrence relation that defines the entire Pascal's triangle. And this is what it would be. And so we have base cases, and our base cases are s of n, 1 is equal to 1, and s of n, n is equal to 1. So the first part means that in any row n, for any row, the first entry, which is this column for any row, is equal to 1. So that defines every single one of these numbers to be 1. And then similarly, in any row n, the nth entry, so the last entry in any row, is also equal to 1. So that defines all of these to be 1. And then a recurrence is that for the nth row, the eth entry of the nth row is equal to the n minus 1th row, so the row right above, the e minus 1 entry, which is to the top left, and then the eth entry, which is the top right. So that recurrence sort of sets that every entry is equal to the sum of the two entries directly above it. And so the key thing to note here is that the base cases have become a lot more complicated, where in the past with the one variable case, you often only will have like 1 or 2 or like a constant number of base cases, versus now you have a non-constant amount. You have to sort of check for any n. So any row, you want to have a base case for each row saying that that row, the first element and the last element are both going to be equal to 1. Cool. Does anyone have any questions about that before I move on? Okay, cool. So yeah, so now we're going to actually move on to dynamic programming. And it turns out that all the things that we've been talking so far are actually ways of doing dynamic programming. And so a formal definition of dynamic programming is optimizing repetitive computations to make recursive algorithms more efficient. And the idea there is that recursive algorithms means like things with a recurrence relation, and optimizing is essentially using methods like memoization and tabulation to sort of make these algorithms more efficient. So the idea is that initially you might have an exponential function like we saw with Fibonacci, and using techniques like memoization and tabulation, you can optimize this to be much more efficient. And so there's a couple of cases where dynamic programming is useful. One of them is called overlapping subproblems, and the second one is called optimal substructure. But more generally, if a problem uses a lot of like recurrence relations and recursion, then sometimes dynamic programming can be used. So the first example is overlapping subproblems, and the idea here is avoiding repeated computations. And an example of this is Fibonacci, which is what we saw with our first problem. And if you remember, we showed a tree here, and more specifically, we found that there are these two regions that were identical, the fib of 2, fib of 1 and 0, and then fib of 2, fib of 1, fib of 0. And this is what we mean by overlapping subproblems, is that there are sort of cases where we have like overlapping regions in the computation graph, and these don't really need to be repeated. And this is where things like memoization and tabulation come in, where you store the values before you actually calculate. And that's one way of optimizing using DP. And then another case is optimal substructure. And so optimal substructure is something we haven't seen yet. We're going to see it on the contest, but we actually sort of saw something related to this in week 3 with arrays. The third example problem was something called flow shop. And the idea behind optimal substructure is that subproblems give you the optimal solution to a problem. So you're trying to find like what the optimal solution at a certain point is. And the optimal solution at a certain point can be calculated by looking at optimal solutions from previous points. So in the example of flow shop, and you'll see more examples of this on the contest, and we'll work through those in breakout rooms. But an example of this is flow shop. And to remind you guys, flow shop, the idea was that you had n swathers and m stages, and you wanted to calculate the time it would take a swather to complete a stage. And the idea is that the recurrence there has two parts. One is that the swather needs to be ready, and then the second is that the stage needs to be ready. And that actually ends up being optimal substructure because you have to take the maximum amount of time between the time it takes for a swather to become ready and the time it takes for a stage to become ready. And that means you're looking at the optimal amount of time, which means like taking the max in that sense. And you will see this more on the contest again. And then finally, how do you actually solve a DP problem? And we've broken it down into 4 steps. So the first one is actually identifying the DP problem. And the common way to like realize something requires DP is to sort of see like a relation between a problem and subproblems. So if a problem seems like it's able to be broken down, or it seems like there's some sort of recurrence relation, then it could be a DP problem. So you want to look for recurrences and ways to define a problem by looking at subproblems, and that's like a good way to identify a DP problem. And then from there, the next step is to actually determine the recurrence relation. And this is on a more mathematical level. So you want to actually break down a problem mathematically and sort of define in a concrete way, like exactly how mathematically you can sort of construct a problem from subproblems. And then after that, you can use either memoization or tabulation and just sort of plug in the recurrence relation directly. And then, of course, you have to remember your base cases just so that you don't, just so that that's sort of like your stopping points where you end the problem. And then after that, you can just code your solution. Cool. So now we're going to move on to the second example problem called permutation descent counts. And Jacob is going to lead this problem.
Okay, cool. Take a moment to read it. I will just steal your screen in a second. All right, so in case you're wondering about like what is a permutation, first of all, or like how should I think about descents in a permutation? The way I like to think about permutations in this context is as like a landscape. So like a sequence of mountains of different heights. And then the meaning of descent becomes clear because when you're walking from left to right across this landscape, a descent is any time that you take a down step. And yeah, so the formal definition of a permutation is that it's a shuffle of 1 through n. I guess the truly formal definition is that it's a function from one to like a 1-to-1 and onto function, a bijection from 1 through n to itself. But you can think of it as just a shuffle of the numbers. It's like you write each number on a card, you rearrange it, any order is a valid permutation. So that's just to get you started thinking about permutations. I recommend drawing these sorts of graphs. If you have your other ways of visualizing permutations that you like, go ahead. But I think drawing these bar graphs is helpful for thinking about this particular problem. All right. All right, so hopefully you got some time to think about this. I think the problem is not easy for sure, and it helps to consider like small cases and try to form a recurrence relation by observing those. So firstly, I think this data is given to you by the problem statement that like the number of permutations of length 3 with 0 descents is 1, with 1 descent is 4, with 2 descents is 3. Or sorry, with 2 descents is 1, my bad. And you can just kind of figure this out by writing them all down. But it would be nice if there was like a more systematic way to like say figure out these numbers from like the previous row of numbers, just like in Pascal's triangle, where each row of numbers is determined like, in fact, each number in each row is determined by the pair of numbers that are like directly above it in the previous row. And it turns out that there is a relation like that for these numbers as well. And the way to get to there is thinking about like how you can go from a permutation of length 3 to a permutation of length 4. So how would you go from like a permutation of 1, 2, 3 to a permutation of 1, 2, 3, 4? The easiest way is to put the 4 somewhere in the permutation that you already have. And you actually have 4 options for doing that. And some of those options will have the same number of descents. Some of those options will have 1 more descent. So for small numbers, like that's what this process looks like. So you start with the 1 permutation of length 1, and then you can insert the 2 either at the beginning, and since the 2 is bigger than every number in the previous permutation, this gains another descent. Like you keep the previous permutation intact, you put the big number at the beginning, and you gain a descent. You could also put the big number at the end, and you'll never get a descent that way because, like, again, the earlier permutation is intact, and then the last step that you created is not a descent anymore. And then similarly, you can do that to get from all permutations of length 2 to all permutations of length 3. It's important to note that every permutation of length 3 only has 1 parent of length 2. And that's because if you remove the 3, you get a unique permutation of length 2. And that holds for n in general. So now there's some more cases. So if you insert the 3 in the middle of the 2 and the 1, then like you're breaking up a descent into first an ascent and then a descent. So the number of descents actually stays the same. But if you insert the 3 from like in between the 1 and the 2 in this permutation, now you're breaking up an ascent into an ascent followed by a descent again. But so you're creating a descent where like none existed previously. So in this case, the number of descents will go up by 1. And in fact, oh yeah, like here's an example with going from 3 to 4. And it shows all 4 of those cases in one permutation. So you could put it in the front, you could put it in the middle between like numbers that are not a descent, we could call that an ascent. You could put it in the middle between like breaking up a descent, or you can put it at the end. The first 2 cases cause the number of descents to go up by 1, and the second 2 cases don't change the number of descents. And that's what that looks like here. It's like basically like, yeah, you can think of this as like we're putting in the biggest mountain in the range, and it will always dominate the thing to the right of it. So the question is, was the thing to its right like previously already dominated by the thing to the left, or did it used to be like going up from the thing to the left to the thing to the right? Okay, right. So using this, how can we get to that recurrence relation that we wanted for calculating the number of permutations with a given amount of descents? Like in some sense, this is like the forward version of the problem, but like the one that you're trying to solve is like the inverse version of this. So what we observe is that like from looking at this set of rules, like the number of permutations that say of length 4 that you create from a permutation of length 3 that have one more descent is just determined by the number of, well, like there's one spot at the front plus the number of spots in the middle that are not descents. So that ends up being like 1 plus 3 minus the number of descents. So it's determined by the number of descents. Similarly, the number of permutations that have the same number of descents, like that you can create by inserting the 4 in this one, is also determined by the number of descents in this permutation. So this is what that looks like visually. So let's say we're trying to figure out PDC of 4, 2. So in other words, the number of permutations of length 4 that have 2 descents. So every such permutation came from inserting a 4 in a permutation of length 3. Furthermore, inserting the 4 can either add a descent or keep the number of descents the same. So therefore, we should look at permutations of length 3 that have either 2 descents or 1 descent. There are 4 permutations of length 3 that have 1 descent, and each one creates 2 permutations, like 2 corresponding permutations of length 4 with 2 descents. And then there's 1 permutation of length 3 with 2 descents, and this one you get a lot of freedom for where you can put the 4. So there's that this one actually is responsible for creating 3 permutations of length 4 with 2 descents. So, all right, are there any questions up to this point? Should probably open up the chat. Feel free to ask in the chat. All right, I will keep going though. Interrupt me at any time. So, summary. You can insert at the front. You can insert in any of these n-1 minus v inner locations, like gaps between 2 elements that aren't descents. Excuse me. You might want to think a little bit about why this is n-1 minus v and not like n minus v. It's because like if there are n things in a row, then there are only n-1 gaps between 2 things. And you can put the big number, put the n+1 into a descent. That won't change the number. You can put it at the end. That won't change the number. And so you get to this recurrence relation, which is the number of permutations of length n+1 with v descents is, okay, well, like first the cases where inserting the n+1 didn't create a descent, and that is PDC of nv times v+1, right? V descents plus the end. Or we could have inserted the n+1 in a way that created a descent, and in that case we would get nv-1 like times n minus v, because that's n-1 minus v plus 1. Okay, but now that you're here, now this dp recurrence relationship is pretty simple to calculate. You just set up a, well, you can do it memoization, or you can set up a 2D array, or you could just set up a 1D array and like iterate on n. And so like implicitly, you know what n is for that array. I think that's how I did it. Yeah. Are there any questions? I guess another way you could think about this is that you could imagine removing the biggest element and see, like, I guess how many descents there would have been in the previous one. I personally think it's a little bit easier to think in the forward direction, but yeah. Please ask questions. Chat is fine. You don't have to unmute or whatever. Okay. Oh, I had a poll, but I think it's too late for the poll. The poll was about permutation descent counts. Wasn't anyway. Okay. We will move on. So here's a memoization solution. This code is like quite short. The mod step. Got to be careful about the mod step. So we're using long longs here because numbers that are mod this 1 million-ish number, when multiplied together, could be as big as 10 to the 12th. That does not fit in an int, so use long longs. Although, now that I think about it, you don't multiply this thing by very big numbers. It might fit in an int if n and v are small. I think n and v are actually like quite small. So perhaps multiplication and ints, that's like not a huge concern. But these numbers are going to grow humongous, right? If you're just calculating factorial, like, you know that those are going to get huge. And these numbers are only slightly smaller than factorial, right? Because like the sum of PDC nv over v from 0 to n-1 is n factorial. That's all the permutations. So these are gigantic numbers. That's why we take it mod. And you should remember to take it mod every time instead of first calculating the thing and then modding. That will get you in overflow trouble. Actually, because, yeah, that will get you in trouble. So cool. Yeah, this is the parts of the memoization solution. Quite clean. But tabulation is fine too. All right. Thank you everyone for coming. We're going to open up the breakout rooms again for the contest. Please give us feedback here. Give you all a minute to fill out the feedback form. And pause the recording. Okay, so congratulations everyone. This is the end of the teaching section of your final Intro to Competitive Programming workshop. You have completed the first stage in the competitive programming journey, and you're on your way to Contest Glory, CodeSprint LA, and all of these other contests. So, woohoo! Give yourself a pat on the back, and enjoy the rest of the ride. Your journey is only beginning. Bruin Quest this weekend. Come out to Bruin Quest. Join the Discord. All the info is distributed through the Discord. And we're going to be holding office hours tomorrow from 1 to 2 p.m. to work on these problems and anything else you might have concerns or questions about. This is part of our initiative to be more inclusive and like accommodating. Finally, mini contest in 2 weeks. A week from now is Thanksgiving. happy Thanksgiving or pre-Thanksgiving, everyone. If I don't see you until then, have a good one and have a go at the contest. We'll be around. Please stay and join the breakout rooms. I think this is like the fun part of the workshop. Cool. All right, I'm gonna end the recording. This will be our last recording.